So students, as you see in this video, limits are back. So we're going to revisit limits a little bit, and we're going to talk about the properties of limits. And so before we jump into the properties, let's just take a look at things that we already know to be true about limits. So what do we know about limits? First, we know what a limit is. A limit is a y value that is being approached. The key word is approaching the particular y value, so it doesn't have to be a function value. And you're looking for that y value where? On a function. And where do you look? You're looking on the function as you approach a given x value. Second thing we know to be true about limits is a limit only exists if the left and right limits agree. And there can be no unbounded behaviors. So vertical asymptote or graph going off to infinity or negative infinity, limit would not exist. A third thing we know about limits. How do you find limits? Well, you can find them by examining a graph and looking at the left and right limits. You can examine limits by creating a table of values and looking at the values coming from the left and from the right. Or you can find limits analytically. So using our strategies of direct substitution, factor reduce, rationalizing the numerator or denominator, all those various strategies that we learned to manipulate a function to see whether or not the limit exists when we don't have a graph or a table. Another thing we know about limits. Limits are the foundation of the calculus course. Everything is built on limits. And the fifth thing we know about limits, which is your AP score, the derivative is a limit statement. So we built the course on limits, and then on top of that we put derivatives, because a derivative is basically a special limit statement, or it is a limit statement where you're finding the limit of a difference quotient where the denominator approaches 0. So those are things we know to be true about limits. And now we're going to look at properties that determine how we find limits of particular functions. So our objective is that students will be able to apply the properties of limits in order to evaluate them. Now, the first thing you need to know about these properties, because if you're looking ahead, you can see that we're going to be looking at finding limits of functions that are comprised of either adding, subtracting, operating somehow on more than one function. So the first thing so we have conditions. It's not a theorem, but there is a condition under which these limits properties apply. So understand that here's the condition, the limit as x approaches c of a function. So we have a function who's named f of x, and if the limit as x approaches c is a number whose name is L. So meaning that the limit as x approaches c on this function does exist, and it's a number L. And the limit as x approaches c on a different function, g of x, gives you a y value of m. So the bottom line is that the limit as x approaches c on both of these functions exists because L and m are both real numbers. Bottom line, the limit as x approaches this particular value of x on these functions must exist in order to apply these properties. If not, then let's take a look at some of the facts about limit properties. Fact number 1, the limits, as I just said, must exist for each function in order for these properties to apply. That's what I said, and you'll see that as we do some of the examples. The second fact is that if the limit does not exist for one or both functions at the particular value of x that's being given, you must examine the one-sided limits, meaning you have to examine, just like we did before when we were learning about limits, the limit from the right and the limit from the left to determine if the overall limit exists. And then the third thing, we unpack these properties, what you'll hopefully notice is that it's not really an order of operations, but it's sort of an order of operation thing. Limits come first and then the other operations. So keep that in mind as I start talking through these various properties. So take a look at property number 1, which is applying to addition and subtraction. So you can see that I'm finding the limit as x approaches c of the sum or difference of two functions. So we have added f and g together or subtracted them. So if we think of, like I said, sort of like the order of operation thing, when we have this sum or difference, what we can do instead is that we can find the limit as x approaches c of the first function, the limit as x approaches c of the second function, and then add or subtract those limits. So find the limit first of each function, then combine by addition or subtraction. The second property says if you have a constant multiple, in other words, I'm finding the limit as x approaches c of a number, this is a number k, being multiplied by a function. So k is a constant. Instead, what we can do first, as I said, think order of operations right here. We're going to find the limit first of the function as x approaches c. So we're going to do that first. And then secondly, we're going to multiply by the constant. Third property, same thing in almost every case. We're finding the limit as x approaches c of the product of two functions. Now, don't think product rule. We're not taking derivative. These are simply limits. Instead, the order of operations things, let's take the limit as x approaches c of the first function, then take the limit as x approaches c of the second function, and secondly, then we're going to multiply. So find the limit first, then apply the operation. For the third property, here we go with division. Let me slide this down a little bit. So for division, we have the limit as x approaches c of a quotient. And so it is division. This is not the quotient rule. We're not finding the derivative. Instead, we're going to find the limit as x approaches c of each function first, and then do the division. And of course, the limit as x approaches c of g of x cannot equal 0, because then we would have, because division by 0 is undefined. All right, number 5, if we have a power on a function, so the limit as x approaches c of a function raised to a power right here. Think of the order of operations. We're going to find the limit first as x approaches c of the function, and then raise to the power. So again, sort of think of this as an order of operation thing, limit first, then operation. And then the sixth one is a little tricky, and it'll make more sense, I think, when you see an example. If I have a composition of functions, so as you can see in this example, right here here's the real problem. The limit as x approaches c of f of g of x. So g of x is the inside function. No, we're not doing the chain rule. We're not doing derivatives right now. And f is the outside function. So first of all, the first thing we're going to do in this case is we're going to work on the inside. So we're going to find the limit as x approaches c. This is the first thing we do. There's the inside function. And we get a y value of L. The second thing that we do, so here's first thing, and the second thing is, notice right here, this is what's a little bit tricky. Now we're going to bring that y value that we just found, that's going to be our new x value approach for the outside. So instead of x approaching c, now x is approaching L. So the first thing is to find the limit as x approaches c of the inside, get that value, and then find the limit as x approaches that new value of f of x. It's a two-step process, so this would be the second part of the process. All right, so in the example that you have here, there's nothing really to do, just an example of how we're going to tear these things apart when we're finding limits. So here is the original problem right here. We're finding the limit as x approaches c of one big old grand function. But instead, we're going to use all these properties. So notice I'm going to do limit first. So I'm going to do limit as x approaches c. So 3 times limit as x approaches c of x, so I can get that x all by itself, and that's that constant rule above, multiply it by 3, plus the limit as x approaches c of f of x. So really all I'm doing is find the limit as x approaches c of each part. In the denominator, limit as x approaches c, the exponential rule, find the limit as x approaches c of the function and then square it. And so the properties that we see basically being applied here, not that I'm going to ask you really to name these properties, but in the first thing I see is the term by term property, meaning that I find the limit as x approaches c of each function and then add them. I have the constant property, meaning I'm going to multiply the 3 after I find the limit. I have the division property. All the properties are here. All right, so let's really see what this boils down to and what does it look like when I am trying to apply these various properties. I'm going to slide this down a little bit more. All right, let's take a look at example number 1. Excuse me. In this example, we don't know what the function f of x is, and we don't know what the function g of x is. We just know the limit as x approaches 3 on these 3 functions exists. And so we're going to use this information to find the limit of some functions that we're actually going to put together. All right, so when I'm trying to find the limit, think of that order of operations. So for this first term right here, that can use the constant property, and I'm going to have that be 2 times the limit as x approaches 3 of f of x. Then I'm going to subtract. I'm going to use the constant property again, 4 times the limit as x approaches 3 of g of x. So there's my rewrite using the properties. In the prompt, they tell me that the limit as x approaches 3 of f of x is equal to 8, so I'm going to replace that. The limit as x approaches 3 of g of x is equal to negative 2. So that gives me 16 plus 8, which is 24. And so that's how you handle that one using the properties. Now maybe for letter B you want to stop the video, try it yourself, or for C or whatever, but the rewrite on this one. Remember order of operations, we're going to do the limit first. There's the constant rule. Limit as x approaches 3 of the function. And then remember what we said, we're going to square afterwards. So we're going to find the limit first, and the limit as x approaches 3 of g of x is negative 2, so we have 2 times negative 2 squared. 2 times negative 2 is negative 4. Square that, and we get positive 16. For letter C, my rewrite for that one using the properties is going to be the limit as x approaches 3 of f of x to the 1/3 power. So notice that takes care of that first term. I changed the cube root to the 1/3 power. I'm going to find the limit first, plus 4 times the limit. There's the constant rule. X approaches 3 of h of x. Oops, I was making that one fraction. That's 2 independent fractions. And then in the denominator of the first fraction, limit as x approaches 3 of g of x. And in the denominator of the second fraction, limit as x approaches 3 of x plus 7. All right, so the limit as x approaches 3 of f of x is 8, so that's 8 to the 1/3 power. Limit as x approaches 3 of g of x is negative 2. Limit as x approaches 3 of h of x. So pretty much this is going to be 0, but I got to make sure the denominator is not equal to 0. So the limit as x approaches 3 of x plus 7 is 10. So that whole thing turns out to be 0. That's not canceling. I'm not dividing. I'm just saying that turns out to be 0. The cube root of 8 is 2 over negative 2 is equal to negative 1. So those are the first examples. Now in the second set of examples, what you're going to see is, I think we go to the second set of examples. Turn the page. Yeah. So now instead of being given just 3 simple facts, we are actually given graphs. And I'm going to make this a little bit smaller, hopefully, so I can see the questions as well as the graphs at the same time. Yeah, that's better. So I have 2 functions. One is f, one is g. Neither of these functions is continuous everywhere. So we'll see how that plays out when we're finding our limits. So letter A, determine whether the following limits exist. If they do, then find the limit. So here's our created function that's comprised of some operations on f and g. So I'm going to break this apart and make this the limit as x approaches 0. Oops, there's my constant rule 2 in front of, f of x, and then we will do the squaring, plus 3 times the limit as x approaches 0, excuse me, of g of x. So I'm going to look at the graph above. The limit as x approaches 0 of f of x. Here's my f graph. And the limit as x approaches 0, I think you can hear my dog in the back playing with her toy. All right, so there's x equal to 0, and from the left, I'm approaching a y value of 2, and from the right, I'm approaching a y value of 2. Therefore, the limit as x approaches 0 is 2, plus the limit as x approaches 0 of g of x. Here is, let's change that color. Here is 0 on g of x, and you can see from the left and from the right we are approaching a y value of 0, so that's going to be 3 times 0. 2 squared is 4, times 2 is 8, plus 0 is 8. So the overall limit is equal to 8. All right, let's jump over letter C. Well, no, we'll go ahead and do letter B. I'm not going to necessarily do all of these, but because there are 2 in particular that I want to get to. But let's go ahead and take a look at letter B. In letter B, I have a product in the numerator. I have a power in the numerator. So we're going to find, my rewrite will be the limit as x approaches -3 of x squared, because that's an actual function, multiplied by the limit as x approaches -3 of g of x, divided by the limit as x approaches -3 of f of x. All right, I'll carry this to the side and then I'll clear it when I go to the next problem. So if I use direct substitution to find the limit as x approaches -3 of x squared, I'll substitute the -3 and that'll give me a 9 multiplied. So now I'm going to find the limit as x approaches -3 of g of x. -1, -2, -3 is right here, and that is a y value of 1, divided by the limit as x approaches -3 of f of x. So 1, 2, 3, f of x, that's -1. So the limit overall is -9. All right, I'm going to clear the screen, do letter C, and then I'm going to jump into, I don't know what I'm going to do. We'll see. We'll see what I decide to do. So let's clear these annotations. So here we go, letter C. This is a composition of functions. So remember what we said is that the step 1 is to find the limit as x approaches -3 of the inside function. That's step number 1. So the limit as x approaches -3 of the inside function, we're working with that, which is right here, and we get a y value of -1. Now remember that -1 goes on to, becomes the approach, so limit as x approaches -1 of g of x. So now we go to the outside and we bring that original limit as the new x value approach. So the limit as x approaches -1 of g of x, which is right here. Now remember, the limit does exist, even though there's a discontinuity, because from the left and from the right, we are approaching a y value of 1, so the overall limit is 1. Letter D is also an inside-outside function, so the inside function right here is x squared, and the outside function is g, so we're going to do, again, I would suggest hopefully you're stopping the video and you're trying to see how you can do without my guidance on this. So I'm going to do my rewrite is going to be the limit. My first step is going to be limit as x approaches -1 of the inside function. And so direct substitution tells me the limit as x approaches -1 of x squared is 1. And then my second problem is going to be the limit. Remember, we're going to bring that last limit as the x approach. So limit as x approaches 1 of the outside function, which is g of x. And if I go back up to my graph, the limit as x approaches 1 right here on the graph is a y value of -1, and so that is the overall limit. Now, before I do the next problem, I would like for, I'm going to clear these annotations, I would like for you to notice, oh, I know what happened. I had actually, what I want you to do is what I'm doing right now. I want you to get rid of the from the left. I want you to change this to limit as x approaches 1 overall. So make that change on your paper, and we're going to talk about what happens in this particular situation. All right, so I'm going to do my write-up. So I'll have the change colors. I will have the constant property, 2 times the limit as x approaches 1 of f of x divided by, start on the inside, limit as x approaches 1 of g of x squared. All right. Now let's look at the limit as x approaches 1, positive 1 on f of x, which is right here, which is a problemo, because the limit as x approaches 1 of this function does not exist. So we said our limit properties are contingent on the fact that the limit must exist, and if the limit does not exist, I said we are going to have to approach from the right. I should have written that on the right instead of on the left. So we need to approach both from the left as well as from the right and see if we get the same value. So if we approach from the left-hand side, we're basically doing the same thing, except for we're going to have 2 limit as x approaches 1 from the left side of f of x divided by limit as x approaches 1 from the left side of g of x. So let's see what happens now. So when we go to the graph of f, the limit as x approaches 1 from the left side, which is right up here, is a y value of 2. So we get 2 times 2. The limit as x approaches 1 from the left side of g is this side over here. So if we're coming in from the left side, we are approaching a y value of -1, and we get -4 as the left limit. Now we're going to compare that to the right limit and see if the two limits agree with each other. If they agree, then the limit exists and it will be that number. If they do not agree, the limit will not exist because the left and right limits do not agree. So 2 times the limit as x approaches 1 from the right side of f of x divided by the limit as x approaches 1 from the right side of g of x. So now when we come back over here to the first graph, f of x, the limit as x approaches from the right hand side, so now I'm coming in from, I get a y value of 0. So 2 times 0 over, and the limit as x approaches 1 from the right-hand side on the g function is still approaching a y value of -1, but the limit turns out to be 0. Now, since -4 is not equal to 0, the limit does not exist because the right and left limits do not agree. Now, if I were a student, I would wonder, well, if the limit's not going to exist, like going all the way back to here, look right back here where I already said earlier that the limit as x approaches 1 of that function did not exist. It seems to me that if that happens, that the limit for the new function would never exist. So I've pulled another example for you to show you that sometimes it does. So let's take a look at this. This is not on your paper if you're in my class. It's not in your notes. So let's take a look at this new example that I pulled for you just for the... So in this next example, you'll see that just because the limit does not exist for one of the functions does not necessarily mean that the limit will not exist for the new function that has been created by a combination of operations. So let's take a look at the example that we see right here. We are finding, and this one's not in your packet, so you're probably going to want to copy this down. The limit as x approaches 2 of this function right here. So over here on the left-hand side, you can see that we have a function whose name is f of x, and that at x equal to 2, there is a discontinuity, and you can see that the limit coming from the left and the limit coming from the right do not agree. So in other words, the limit as x approaches 2 of f of x does not exist because the left and right limits do not agree. So since we know that that's going to come into play here and we're going to have to find the one-sided limits, let's just go ahead and do the one-sided limits, because this piece right here is going to be a does not exist, and we said that if the limit does not exist for one of these functions, then we have to go back and we have to if the limit does not exist, then one of our criteria for the properties is that the limit must be a real number. So we're going to need to do one-sided limits. So I'm going to clear the annotations and oops, edit, undo. That's not what I meant to do. Let's clear the annotations. And so if we have the limit, so I'm going to do the left limit from the left. So the limit as x approaches 2 from the left side, and we're going to take this thing apart and work on the inside first. So we'll have the of f of x working on the inside minus the limit as x approaches 2 from the left side of 1, and that gets squared, minus the limit as x approaches 2 from the left of 6. All right, so this is going to be the left limit, and so the limit as x approaches 2 from the left of f of x, that would be coming from this side, is a y value of -2, and the limit as x approaches 2 from the left of 1 is going to be, oh no, that's -1. Sorry, let's fix that. That's not -2. So the limit as x approaches -2 of f of x is -1, that's the y value being approached there, minus the limit as x approaches 2 from the left of 1 is 1, and then we're going to square that, minus the limit as x approaches 2 from the left of the constant 6 is certainly going to be 6, so that gives us -2 squared minus 6, which is 4, minus 6, which is -2. All right, let's take a look at the limit coming from the right side. So we're going to do the same thing, except for this time it'll be the limit as x approaches 2 from the right of f of x minus the limit as x approaches 2 from the right side of 1, and that quantity is squared, minus the limit as x approaches 2 from the right side of 6. Hopefully you can see the 6 there. All right, the limit as x approaches 2 from the right side is here, so we're approaching a y value of 1, 2, 3, minus the limit as x approaches 2 from the right side of 1 is going to be 1, and we're going to square that quantity. The limit as x approaches 2 from the right side of 6 is going to be 6. 3 minus 1 is 2, 2 squared is 4, 4 minus 6 is negative 2, and so we have left and right agreement. So since the left and right limits do agree, we get a, I've got 100 phone calls since I started doing this video. Since the left and right limits do agree, the overall limit is going to be equal to what those two are, which is a y value of negative 2. All right, so that gives you an opportunity to see how just because a limit doesn't exist for one of the functions doesn't mean it's not going to exist for the overall, and you do need to take it apart, the left and right limits. So this is your video on properties of limits. Next example, you will see that